In the last video, we talked a little bit about Gauss's law and motivated this idea of electric flux. In this video, what we're going to do is we're going to define electric flux, and we're going to talk a little bit about the different properties of the field and the surface area that come into play when you actually have to deal with it. So the way we're going to talk about this is in terms of thinking of a flat surface at first. And so over that flat area, which has a total area A, there might be some electric field that we can measure on the surface. And so maybe that electric field looks like this. That is, these are the individual field vectors at every observation location. And so maybe they look like that. Now, the way that we define the electric flux, which I'm going to write in terms of this phi, and I'll indicate it with this this E here because there will be magnetic flux in future classes that we'll talk about. The way that we define it is as an integral of the electric field over some area. Now, that's because the electric field can change its value. That's because the orientation between the electric field and the surface can change. And also, the particular surface could be shaped differently. The size could be different. So we have to sort of generally define it in terms of an integral over some whole surface, right? Now, the units of this thing have units of electric field, which is newtons per coulomb, times units of area, which would be meters squared. So it's a Newton meter square per coulomb. It's also a voltmeter, which is the units of electric potential times a unit of length, which it turns out to be the same units as flux. Now, sometimes when this electric field is oriented just right and the surface itself is sort of has a particular kind of flat orientation with respect to the electric field, that is, you know, the electric field is the same everywhere and the surface doesn't change its shape. Sometimes we can define this as the electric field dotted into the total area. Now, the problem with writing all of this is that you're probably asking, well, what is this dA vector? What is this A vector? So, you know, what are these things? What is dA? And these are what we call area vectors. And they're essentially vectors that describe the orientation of the surface with respect to some other geometry that we have, right? So some specification of the coordinate system, for example. So in the case of a flat surface, what we say the dA vector is, it's the vector that points perpendicular to the surface. So, you know, it might point in the positive z direction, it might point in the positive x direction, it might point in some combination of those, but it points perpendicular to the surface, and depending on what your coordinate system actually is, it might be that that dA has different kinds of components. So it's perpendicular to the surface everywhere, which means that at every point on this flat surface, it actually points in the same direction. That's really, really useful, and it sort of hints at the fact that we can do this very straightforward calculation of the electric field times the total area. We'll talk about in the next video in some cases when the surface is sort of curved like this, that dA vector will point in different directions depending on where you are on the surface. And in that case, it might not be as straightforward as doing this kind of calculation. This is why I said that this equality only holds sometimes. Now, this flux idea depends on several quantities. First, it depends on the electric field strength. So how strong the electric field is at the location of the surface over which you're dealing with it. The other thing that it depends on is the size of the actual, size and shape really, of the area that you're concerned with. So is it a flat shape? Is it a curved shape? How big is it? And so forth. And the last thing it depends on is actually the direction of E relative to the area vectors. And this is the one that I want to spend a little bit of time talking about in this video because it depends on whether the electric field points sort of perpendicular to the surface or whether it has some angle that it makes with respect to the surface and so forth. That will really influence the flux calculation. So just for that one, let's just take that as its own sort of deal, and we'll compare two electric fields over the same area. So let's say we have this flat surface, right, where we know all of the dA vectors point up like this. And let's say in this case we have an electric field E that points also perpendicular to the surface. So this electric field has some strength. It's, you know, the magnitude of E, but it points perpendicular to the surface everywhere. In this case, this is the very simple case where the flux is just E dot dA integrated, but because the orientation of the electric field is the same everywhere and its magnitude is the same everywhere, this is really just the magnitude of the electric field times the total area of this shape, right? So that tells you that this is the simplest case. It's the one that applies when E dot dA are oriented in the same direction. Another case that we can have, same flat surface, same dA vector. We have the same electric field, and by that I mean it's the same magnitude, but now let's say that that electric field makes an angle with respect to the vertical of theta. So if that electric field makes an angle with respect to theta, which is oriented with respect to the vertical here, that flux is going to be smaller, right? There's not as much electric field sort of going directly through. There's some skidding along the surface here, right? And our calculation of the flux should represent that. There's a little bit less electric field going through the surface than in the first case. And it turns out that it does. It works out just fine because that definition of E dot A, which still works because the electric field is actually pointing at that angle theta everywhere. So the orientation is the same relative to the surface. It's just that it's not as much. So that tells us that that dot product is going to pick up this cosine theta here, which is the angle that the electric field makes with respect to dA, or with respect to the perpendicular dA vector that points perpendicular to the surface. So we still have that EA business, which was in this case, but now it's modified by cosine theta, right? It's multiplied by cosine theta, which is often smaller than 1, with the exception of when the electric field points in the exact direction of dA. So these two cases here are meant to demonstrate that the direction of E relative to A matters. In a couple of other cases that we'll work on in the next couple of videos, we'll talk about how the size and shape matters, and we'll talk a little bit about how the strength comes into it.